Hello everyone, my name is Audrey Long and I'm going to be talking to you guys about the HeartBleed exploit. Before we jump into it, let's go over the quick overview. So today we're going to talk a little bit about OWASP Top 10 and do a little bit of a deep dive into the sensitive data exposure. We're going to go into some HeartBleed overview along with a very quick stack and heap overflow, do some of the source code analysis, see the HeartBleed results, and then some sensitive data exposure mitigations. All right, so many of you have probably seen the OWASP Top 10 before, but if not, just to go a brief overview, the OWASP is an open web application security project. It's an open community dedicated to enabling organizations to develop, purchase, and maintain applications and APIs that can be trusted. The OWASP Top 10 is a standard awareness documentation for developers and web application security in general. It represents a broad consensus about the most critical security risks to web applications. Going into that, we're going to go a little bit more into the sensitive data exposure side of the house. So HeartBleed falls into A3 of OWASP Top 10, and it's dangerous because it exploits the ability to exfiltrate the sensitive data that's stored within the web server. Many web applications and APIs do not properly protect sensitive data, such as financial data, healthcare data, and personal information. And attackers may steal or modify such weak protected data to conduct credit card fraud, identity theft, or other crimes. Sensitive data may be compromised without extra protection, such as encryption at rest, encryption in transit, and requires special precautions when exchanged within the web browser. All right, so let's get into what is HeartBleed. So HeartBleed is a security bug that was found in the OpenSSL cryptographic software library. It's a robust high-end commercial grade toolkit for the TLS and SSL protocols. It's also a general purpose cryptographic library. It's widely used by internet servers, including a majority of HTTPS websites. It was introduced into 2012 and publicly disclosed in April of 2014. HeartBleed may be exploited regardless of whether the vulnerable SSL instance is running as a TSL server or a client. It results from improper input validation due to missing bounds checks and the implementation of the TLS Heartbeat extension. Thus, the bug's name derives from heartbeat. The vulnerability is classified as a buffer overread, a situation where more data can be read than should be allowed. All right, so before we get into the source code analysis, let's have a very quick and brief stack and heap overflow. So what is the stack? A stack is a special area of the computer's memory, which stores temporary variables created by a function. In the stack, variables are declared, stored, and initialized during runtime. It is a temporary storage memory where the computing task is completed, the memory of the variable will be automatically erased. The stack section mostly contains methods, local variables, and reference variables. All right, so on the flip side, what is the heap? The heap is a memory source used by programming languages to store global variables. By default, all global variables are stored within the heap memory space, and it supports dynamic memory allocation, such as your mallocs. The heap is not managed automatically for you, and it is tightly managed by the CPU. It's more like a free-floating region of memory. So some key differences include the stack is a linear data structure where heap is a hierarchical data structure. Stack memory will never become fragmented, whereas heap memory can become fragmented as blocks of memory are first allocated, then freed. The stack accesses local variables, while only heap gives you access to the variables globally. The stack can't be resized, whereas the heap resize can happen. The stack memory is allocated in a contiguous block, where the heap memory is allocated in random order. The stack does not require to deallocate variables, where in the heap, you need to deallocate your variables. All right, so enough of that. Let's get into what is buffer overread. So as you can see, this is not a buffer overflow, and instead this is a buffer overread. So what are the differences? Well, in a buffer overflow, buffers are memory storage regions that temporarily hold data while it's being transferred from one location to another. A buffer overflow or buffer overrun occurs when the volume of data exceeds the storage capacity of the buffer. As a result, the program attempting to write the data to the buffer overwrites adjacent memory locations. So what is a buffer overread? A buffer overread is like a buffer overflow, except it occurs during a read operation, whereas a buffer overflow occurs during a write operation. While reading from a buffer, the program goes over the buffer boundary and then starts reading adjacent memory. The root cause of buffer overread is similar to that of the buffer overflow. It's typically resulted from insufficient or lack of bounds checking for buffers to read. Heap buffer overreads get classified into three main categories. There's the memcopy based, which this is a major type of buffer overread vulnerability, and you'll see why later in our source code analysis, and it's possibly the most damage causing due to HeartBleed. This happens when the size argument of a memcopy function is accidentally or maliciously enlarged so that more information than necessary is allowed to be copied to the destination. The other two memory classifications are string copy based and byte level based, but we'll go over that in another topic. So the root cause of this vulnerability is a buffer overread bug in OpenSSL's implementation of the TLS DTLS heartbeat extension, which is used to test the secure communication links are alive. So let's get more into that later on. All right, so before we kind of jump into it, let's see what you get from the heartbeat response. So essentially, imagine this. This vulnerable heartbeat code is sitting on a vulnerable web server, and a user decides to log into a website at some point. Those credentials get stored in cache, or in this case, on the heap, and a malicious user that can come around the website and knows that the heartbeat bug exists, there's a strong probability that the data that follows the heartbeat request that you're getting from your server contains the user credentials. So researchers have also discovered with the heartbeat bug that the write bytes function call happens so close to other crypto operations that they could actually extract key information from the heartbeat response. If you think about that for a moment, if you're a malicious user and you have a web server and you have all this key information, that means you can decrypt literally all of the traffic from the web server. So here in this picture, you can see an example of how the heartbeat works. So the server sends a 4-letter word. In this case, it's going to be bird. Generally, it's not going to be bird, but the server then reads bird and then heartbeats back bird. But with this specific vulnerability, you can control the size of the data that also gets sent back. So not only will the server respond with bird, but it could respond with 500 extra bytes that follows bird, and who knows where that lies in the heap. All right, so without further ado, let's jump right into the heartbeat function. So reverse engineering and security in general is like solving a really complicated puzzle. It's fun to put your detective cap on and start looking for clues. Well, taking a look at the source code, we should be asking ourselves, now what could be going wrong in our code path? Taking a look at the types, we can note off the bat, all of our variables are of type unsigned, which gives us a clue that we're most likely going to be working with positive numbers throughout the rest of the functions. Not only are comments useful for developers to understand what you're doing, it's also useful for reverse engineers to understand what you're doing as well. According to the comment, read type and payload length first, we can piece together that the first variable HB type, which is located at that 2 over there, is taken from the first byte of the payload. Now, something else to keep in mind is when you're reverse engineering these binaries, you can see a lot of these strings within a reverse engineering tool such as IDA Pro or as NSA's tool Ghidra. So then you can really trace back and see within all of this reverse engineering machine code where a lot of these functions are actually created, which is scary if you think about it. All right, so taking a look at the types, we can note right off the bat that all our variables of type unsigned, yes. So while we kind of explore this further, we will keep that in mind. It can also be noted that the payload length is taken from the packet as well, located at 3. Not only, so this is not displayed here, but under the covers, this N2S function takes the payload and converts it to a short integer. Okay, so just keep that in mind. We didn't really have that much time to go over this, so this is very quick and dirty. Looking further down at the heartbeat request, we can see that the HB type is equal to request, and if that if check follows through, the certain code path will be executed, which we will discover on the next slide. Okay. So we notice that the buffer gets allocated with 1 and 2 and payload and padding. Please note that the payload is supplied by the user, which we saw on the previous slide. And in this case, it's going to be an actual binary file, which we see the pointer gets set to the buffer and the type gets set as a response, which will indicate to the client that a response is being sent from the initial payload. We then take the payload length and convert it with the S2N function, which is also not pictured here under the covers, and place it into the next 2 bytes of the buffer as a short. So essentially, this is taking our length and saying, hey, client, those 2 bytes are representing the length I'm sending you. We then mem copy from the original payload, PL, into our buffer, BP, adding padding if required. Then we write the bytes back on the line R is equal to DTLS1 write bytes. So in this code path, do we see anything unusual? Well, looking at the memcopy function at 4, it copies data of payload size from the source buffer PL, which contains the heartbeat request message to the destination buffer BP. However, since both payload variable and the PL buffer are controlled by the attacker, and there's no check to make sure that the actual length of the PL buffer is equal to the payload, the attacker can provide a very short heartbeat request message while setting the payload value to a very large message, in this case up to 65,536 bytes, which we know is the size of an unsigned short. Thus, the memcopy function will read beyond the boundary and copy sensitive data to the BP buffer, which is eventually sent back to the attacker with the write bytes function call. So looking back up at P1, what if the data represented here is smaller? Let's say 1 byte of data, and then the size of the payload is 10,000 bytes. Then what happens in the memcopy? Well, since P1 has only 1 byte of data, so the data being copied in the memcopy is data that follows P1 in heap space and not tied whatsoever to that P1 that was in whatever it was intended to be. So in short, if attacker can control the payload and control the size of the payload being sent, the attacker controls bytes of memory leaked in a response. Here is why we classify the vulnerability as a sensitive data exposure. It is not a buffer overflow which overwrites data, but rather we're reading beyond the buffer boundary and into that heap space. So the goal of the attacker is to steal information previously used and left in the heap memory. For example, if the vulnerable buffer PL had been used in handling a previous user's request, the data in the buffer cannot be cleared or initialized, and the memcopy will copy such data to the intermediate buffer, which will be sent to the attacker. And that information could include your login credentials that you used to get into that website. So just taking a quick look at this, what was the HeartBleed fix? So the first part of the code, we check to see if the payload that we have is now indicative of the payload that remains, which can cause problems. The second part makes sure the request is actually as long as it says it is. As you can see here, validating inputs are crucial to protecting data leakage along with the OWASP top 10 vulnerabilities and can be easily prevented with code peer review. All right, so some sensitive data exposure mitigations as a whole. So located on this slide are the best OWASP practices to prevent sensitive data exposure. Coverity, Code Sonar can be used to detect the HeartBleed bug as well as other glaring memory and code issues. So what we recommend is actually getting some of those static code analysis tools in your CI/CD pipeline, just to make sure that you are absolutely using all the code that you're writing, you're freeing all the memory, you don't have any weird memory leaks. And perhaps when you're in the code review process, you can spot out right away that, hey, you're not actually doing input validation here. Encrypt data during the transport and at rest. That's very important, just to make sure we're on the same page. The encryption will allow, if the data got leaked, maybe it's harder for the attacker to find out what kind of information you're actually sending. Minimize the data surface area. Use the latest encryption algorithms. NIST has a great example of all of the up-to-date and highly recommended encryption, so definitely check out NIST's website. Disable autocomplete on forms that collect data. Disable caching on forms that collect data, and do some fuzz testing. You know, throw a bunch of random inputs at your code and see how does it respond. All right. Thank you guys so much for listening. I really appreciate everything.